Okay, thank you very much for the invitation. I'm very excited to talk here. And yeah, the title of my talk is Statistics of Integral Points on Conics. Conics. And indeed, I'm going to talk about families of conics, and I will focus today on two questions, namely, when do they have integral points, and for families of conics, when you do know that they have integral points, I will ask whether they satisfy, how do they reduce modulo fixed integer? So if you like some sort of weak approximation for the solution set. So more precisely, I'm going to focus on Pell equations. So Pell equation, x squared minus d y squared is, let me write, plus minus 1. And d here is square free positive integer, let's say at least 2. And well, you probably do know that if I put a plus 1 here, it's well known that there is an infinite set of solutions. However, with minus 1, that is less clear. And here I'm asking how often this is solvable. So the first question I'm considering is for you take a large parameter x, and you count, let's call this equation star. You count the number of d up to x such that star is solvable over z. And you ask how often that happens. And the second question is when I put a plus 1, so I consider the set of, then you do know that the negative Pell, the Pell equation is solvable, but then what I'm going to ask is that I fix a positive integer, let's say also at least 2. And then I'm asking, let me write it, I will give precise statements later, but what I'm asking is the behavior of the set of solution when you reduced modulo C. So let me write a very baby version of the question, for instance. Sorry, x, y, the behavior of the cardinality of the set x, y in Z squared, such that x squared minus y squared dy squared is 1. Reduce modulo C. So you take the set, the global set of solution, you reduce it modulo C, that is a finite set, and then, for instance, you can ask how big that set is, or you can ask more precisely if I vary D, how often I get a certain subgroup, well, it has a structure, but a certain subset, let's say, of Z modulo C, Z squared. So here you know that you have a solution, and then an interesting question is what is the behavior of the approximation of local solutions by global solution. And here the mystery is in how often the equation itself is solvable. Yeah, of the set mod C.
But this is infinite. I mean, there's infinitely many.
No, sorry. Here it's a bit of an abuse of notation. I mean, this is the set reduced modulo C.
So x and y are integers modulo C. Or?
No. X and y are in Z squared, and I take the set of all solutions in Z squared, and then I reduce it modulo C. So this is the, when I write here mod C, I mean the image of the set of solution. Okay, so you have a map from the set of solution x, y, solving the Pell equation. You have a natural map in Z mod, well, in if you like, in OQ root D, the ring of integer modulo C square. Sorry, modulo C. Or if you like, in Z mod C, Z, yeah, so, sorry, maybe I consider, I write it in this form. Let me rewrite it in this form, actually. Let me rewrite it directly. This form. Cardinality of OQ root D. Yeah, thank you. Star mod C. Is that clearer? Yeah, sorry. So how does it work here? I guess I have to do this. Yeah, I don't take X and Y, actually. That was cheating. I'm taking the unit group and I'm reducing it. C is a fixed integer, yeah. Yeah. So those are the two problems I want to focus on. And okay, let me tell you a little bit. One is a problem that had an old history. The second one, I don't know very well the history, so but let me tell you what was known about one. So first of all, the equation x squared minus dy squared is minus dy squared equal 1 is started since the time of Archimedes, but the negative Pell equation was the first work on this was due to Euler and Lagrange. And they knew that star is solvable if and only if root d, the continued fraction expansion. They gave a criterion for the solvability of star in terms of the continued fraction expansion of root d. Namely that the length of the period must be odd, as odd period in continued fraction expansion. Yeah.
I'm still confused. So before you wrote down, solutions of the Pell equation, and now it's just the size of the units. What about things of normal mindset? Is that what you mean? Or is it?
Yeah, here
you include plus and minus.
Yeah, that I will come back on this later, because for as I will explain in a second, in a bit, for 100% of the D's, the Pell equation hasn't a solution. The negative Pell equation has no solution.
Okay.
So if you, yeah, indeed, that's an interesting thing. You could study two within the family, and that would be very, very different. But what I'm going to talk about in two is when, for trivial reasons, which happens 100% of the time, that this equation has no solution, and then you know that the normal Pell equation has a solution, and you're asking where does it go modulo C. It's a very natural question. What are the rules? Like statistically, it's a finite set. So each occurrence, how often do you see it? So that's a very nice criterion from Euler and Lagrange, but it's not very useful to answer, as far as I know, to answer question one. Fermat and Dirichlet could already produce an infinite set. They observed that if D is P, it's a prime, that is 1 mod 4, then star is a solution. So that's already an infinite set where you do get a solution, and as you will see in a bit, that's a very small set compared to how often you expect a negative Pell to be solvable. And actually, this is due to Fermat. It has a sort of a very weird elementary proof, and Dirichlet found a similar subfamily. D is P times Q, so 2 primes, both 1 modulo 4, P and Q, both 1 modulo 4. And with a condition on the Legendre symbol, that P over Q is -1. Then the same conclusion. Yeah, that's a slightly bigger family. And generalizing this work, Cremona and Odoni I think in the 70s, could produce slightly bigger family where you fix the number of prime factors. So D equal P1, PK, and they generalize this. Let me say they generalize this condition. Generalized and produce slightly bigger families. So a little bit before, actually, Nagel made a conjecture, namely that the number of times this equation star as a solution should be a positive proportion of the number of times the same equation as a solution over Q. So let me change a little bit notation and call this star Z, meaning that it's solvable over Z, and star Q will mean that it's solvable over Q, and I will call S Z X the set where okay, let me write it in this way, such that star Z, sorry, let me write it in this way, D less than X, star Z is solvable, divided by the number of times the rational equation is solvable. Actually, Nagel conjecture that there should exist, the limit as x goes to infinity should exist, converge to some limit which is in 0, 1, strictly. I don't know on the basis of what Nagel made this conjecture, and let me tell you, and that goes a bit on what Rachel was asking. So this set is very well understood, the set downstairs. So D star, so the equation x squared minus this y squared over q is minus 1 as a q point. That's very easy if and only if P dividing D implies that P is congruent to 1 or 2 mod 4. And that's because of the Asiminkowski. Because you reduce the equation modulo, the conic needs to have local solutions outside of the prime dividing D it has by Hensel, and then you do the primes dividing D, you reduce it, and you find that minus 1 is a square mod P. So that's a necessary condition, and it's not hard to check that it's then also sufficient to have QP points, and then by Asiminkowski, you know that you get a Q point. So if you do the same, yeah. Here in this talk, I didn't write it here, but I said it. I think this is square. Otherwise, you could add. You're right. Otherwise, you could put 3 square inside the. Yeah. So that tells you already that the cardinality. Okay, I will call that those sets SQX and SZX. I hope, without defining it, spare time. The cardinality of this is asymptotically some constant times x divided by root log x. You are counting square-free integers, all of whose prime factors are 1 or 2 modulo 4. They are either 2 or they are 1 modulo 4. So that shows that star is solvable already over all square-free integers 0% of the time. So that's actually will be quite interesting for 2, because it means that when you study 2, you can neglect the negative Pell equation when you study over all square-free integers. But then basically Nagel is asking if there is a similar formula for SZX. Nagel conjecture is that there exists, that SZX should go as some constant, this is Nagel conjecture, times beta times x root log x. Beta you can make explicit, is a not very beautiful constant. And Blomer actually could improve this result of Cremona and Odoni. Blomer could prove still a 0% result inside this conjecture, but could improve a little bit by showing that it is at least SZX is at least some slightly smaller thingy, like something like, I think, 0.61 or something. So that is still 0% off, but it was much better than these works of Cremona and Ottoni, where you would fix the number of prime factors. Here, Blomer would use all prime factors, like growing number of prime factors, as d grows. And then Stevenhagen came in 95 and made a conjecture which refines. So I think this is about 95. I think that's from the 70s, that's from the 30s, and this is actually a bit more recent, I think from 2000. So Stevenhagen actually, Stevenhagen gave a conjecture for C. So Stevenhagen proposed that, conjectured that you can take C to be 1 minus the product over all j's of 1 plus 2 to the minus j inverse. So these constants look completely crazy, but I hope by the end of the talk you will have some feeling of where it comes from. And that is regarding the problem number 1. And regarding problem number 2, there is an obvious guess that there is an obvious conjecture that you could make that once you fix, let me work over D, the families of D, among those D's, among these for which such that the prime divisor of C, every L dividing C, is inert. I fix the local conditions, is inert in Q root D. That's just a sub case of problem number 2, and then you could study. Then already the fact that the SZX is solvable 0% of the time, is a 0% set, shows that for 100% this set is a norm 1 subset. So you know that when you reduce mod C, 100% of the time you must be norm 1. That gives you already a restriction, and then once you fix this behavior, you are, after doing an identification, you are essentially studying a map from this to the product of L dividing C, F L square star norm 1. So the norm 1 subset of this thing. And then you could conjecture that essentially this is equidistributed, that you get that the fundamental unit equidistributes modulo C. So once in this subset of a norm 1 element. So a plausible conjecture, which probably appears somewhere, I don't know very well where, but a conjecture could be that this is equidistributed. And today I want to talk about results in the direction of 2 and a proof of this conjecture of Stevenhagen. So let me go to the results. There are questions now. I can. Moment. Sorry, I should have taken this. Sorry. Yeah, so first theorem. This is a joint work with Peter Koymans. In this theorem, early winter 2000 of this year, Stevenhagen's conjecture is true. So Stevenhagen conjecture holds, namely, you have SCX is indeed that funny constant, which let me call it for brevity, well, okay, 1 C Stevenhagen times beta x over root log x. Next, joint work with Alex Bartel on 2. So I think Alex will talk about other aspects of this work this week. This is going to be a result that shows, okay, maybe not in the entire thing, but in the norm 1 modulo squares of the norm 1, you do get equidistribution within the family where the double of the class group is odd. That looks a bit funny, but I will explain this better during the rest of the talk. So let me phrase it in this way: probability of, I take d up to x, such that the 4 rank, so this is the double of the class group of Q root D is an odd group, so the size of this thing is odd, and the unit group, the image of the unit group star in, let me call H. H is this group, H of C is this group modulo squares. That group modulo squares, mod squares. So some sort of approximation of the desired equidistribution result. And the image is a given subgroup of order 2 of plus minus 1 plus minus epsilon, where I fix an epsilon in H of C. So I fix a possible place. I want to prove that the probability of getting epsilon is what you expect. This is as the following formula: product from i's to infinity of 1 minus 1 over 2 to the I times cardinality of 1 over H of C. In other words, you get once you fix that the double of the class group is odd, the fundamental unit equidistributes modulo C modulo squares. And let me say, before getting into the details of how some of the details of how these things are proved, let me say sort of the hopes for future works. So as I will explain, this theorem with Peter relies on new techniques that we introduced inside a method introduced by Alexander Smith to control the to infinity of a class group of quadratic fields, more generally prime degrees fields of the, well, then you take the L part, okay, but we introduced, there was a major stumbling block in applying that method to approach Stevenhagen's conjecture, and we expect that with this this new technique, you could approach also the following problems that looks completely unrelated. the so-called Chaulas conjecture over function fields, L chi half is the vanishing of L function at the half point of L function of hyperelliptic curves over a finite field. So you fix Q prime power, and then Chaulas conjecture predicts that this should be 0%. So it should be O of X. And for reasons that are not obvious, this problem can also be approached as a problem about to infinity distribution of certain Selmer group. Yeah.
Could you read out the statement of your second theorem again? It looks
Yeah, so I'm studying the proportion of the D up to X such that two events happen. The double of the class group is O. And the fundamental unit is a fixed element of that group H of C.
So the second part says image of this map.
Oh, sorry, image of the map in H of C is, sorry, equals.
Oh, thank you.
Thank you, sorry. So, yeah.
And so you say probability, so on the denominator, it's just the number of D up to X squared free. Like, yeah. Okay.
Yeah, and indeed I should say that this factor is the probability that the 4 rank is trivial, and this factor is simply saying you get every unit, every local unit uniformly random.
And sorry, and that product starts from I equals 2, and this product starts from J equals 1.
Yeah, that's right.
Right.
And the 2 is really a responsibility of real quadratic fields. Some of these type of products often show up in Cohen-Lenstra heuristics, and somehow you start the rank of the unit group, it's shifted by the rank of the unit group. So the 2 is 1 plus the rank of the unit group of the real quadratic field. And okay, so sorry, yeah, this problem can be studied as a problem of the two part of a certain family of Selmer groups, and the technical problems that you face in approaching these are exactly the same that you would face studying the negative Pell equation. And we have big hopes. We here is me, Peter, and Mark Schusterman to prove this. And that's regarding 1, and regarding 2. Basically, as you will see, this double here, you will see that in the rest of the talk that the 2 torsion of the class group is something deterministic. Then you double the group to get rid of that. And saying that that is odd is a bit as you always have with real quadratics, this dichotomy that you cannot separate the class group from the regulator. And this condition is really to say that you know that there is no class group in some sense. So the hope for the future in future work is to control the entire distribution using more advanced techniques of the shape of this, of one entire distribution of this object. Oh, F2, so that's a quadratic arc, just a quadratic arc. I just take quadratic. Oh yeah, sorry, yeah, discriminant chi. Yeah, I'm sorry, x little o of x, yeah. Yeah. So currently the best result, if you are allowed to move Q by topological methods, you can prove that with the limit of Q going to infinity. But here the game is that you fix Q, and then there is a method of Sarnak and Katz that allows you to prove something like 93%. But so far there is not yet a way to get 0%. 100%, depending what you. And entire distribution of OQ root D star mod C tensor with Z2. Essentially, you look. So somehow to remove this technical condition on the class group, and whatever is the behavior of the class group, you control that the unit group equidistribute, however, only in the 2 part of the group. So these techniques are not able to say much about the tree part of the unit group, but if you take the modulo C, if you reduce this group here, if you decompose it in primary parts, it has a big 2 silo. And essentially in that factor, the goal in the future will be to prove equidistribution of the unit group. So this is inside the 2 silo of product L dividing C FL square star. I should put norm 1. Yeah, okay. So I would like now to explain some of the ideas. This works. Oh, and something else I wanted to say about 1. I think there will be a talk by Adam this week of an analog of the negative Pell equation for elliptic curves. And there is hope that these methods might help you make progress also on the conjectures you will present. Okay, so I said in part 1 that this comes from something about the 2 infinity of the class group, and part 2 you also see somehow the 2 infinity showing up because I'm taking the 2 silo. And now I would like to explain what's the connection, first of all, between the negative Pell equation and the 2 parts of class groups, and which problem we had to solve and which kind of new tool we introduced. And I will say something about the way Alex and I approach this, and Alex will, I think, give a talk that entirely focuses on complementary aspects of the study of part 2. Okay, so what is the connection between the negative Pell equation and the 2 parts of class group? Well, that's quite elementary. So x squared minus dy squared as a solution is solvable if and only if rho d is trivial in the narrow class group of Q root d, which is equivalent to the fact that the narrow class group is actually equal to the ordinary class group. I will briefly remind you of narrow class group in a second, which is in turn equivalent to the fact that the 2 parts of the narrow class group is equal. So this is, by 2 infinity here I mean the 2 silo. You take only the elements of the group that are killed by some power of 2. The 2 part is equal to the 2 part of the ordinary class group. And that's where the connection with Smith's work and the 2 infinity of class group comes in. You have a criterion for the solvability in terms of an equality of just the 2 parts, just a little piece of the entire narrow and respectively and ordinary. There are other equations that are conics which would involve not just the 2 part, but maybe the 3 part, or maybe the entire class group. And to make progress on that, you would essentially need to understand something about the odd part of the class group in quadratic fields, and that's something at the moment, except from a few little results, well, little in the sense of that there are big results in terms of the method, but little in terms of the possibilities of what you should prove. Yeah, very little is known essentially about the odd part of the class group. So somehow there is an accident here at play that this equation, and there are more general equations actually that are more general families of conics that are related to the two parts of the class group. If there is time, I can mention a few later. But there is a little bit of an accident here in this chain of equivalences that allows you to translate this problem into this problem. So maybe let me very briefly say why those are true. So the narrow class group is the group of ideals modulo principal. So this is fractional ideals modulo the group of principal ideals which admit a totally positive generator. So these are ideals of the form alpha, where alpha is totally positive. So it's a little bit refined with respect to the ordinary class group, because there is a requirement on the sign of the generator. So this direction is, this equivalence is essentially saying that root D is trivial, means that you can find the generator of root D, which is totally positive. So to find the generator of the ideal root D, you have to multiply by a unit. And then this must be the alpha that is totally positive. But then that unit must, since root D is positive in one embedding and negative in the other, then to correct that, it means that epsilon must be negative, the norm of epsilon. So that's essentially what is happening. And the other direction also holds. If you can find such an epsilon, you can clean the sign of root D and you make it totally positive. So this explains these equivalence, and it's not hard to see that these groups differ at most. The kernel of the map from this group to this group is generated by this guy, so that's that equivalence. And here happens the crucial step where you get to infinity. The reason is that root D is 2 torsion. So root D square is D. This is D, which is certainly totally positive. D is D in both embedding, which is a positive number. So this is trivial. So that means that these two groups differ by an order 2, at most order 2 element. So the only thing that matters is the 2 part. The odd part doesn't play any role. Okay, very good. So then that's the connection, but then how are you going to use this connection to prove that limiting statement? So the idea is the following. So let me start with the fact that the equation over the rational is solvable, x dy square is solvable over Q. You can rephrase it in terms of the class group as follows: if and only if root D is at least a double in the class group, in the narrow class group, is in 2 times. This is not hard to prove. So the idea to study then SZX, the idea is that the difference, to move from SQX to SZX, you have to do an infinite process where you check, okay, now it's a double, so at least it has a rational point. So now I check if it is a multiple of 4. If it is not a multiple of 4, it's not going to be trivial. And then the equation is not solvable. If it is a multiple of 4, I continue. I check if it is a multiple of 8 or not. And then I get better and better approximation to the limiting constant predicted by Stevenhagen. So that limiting constant actually shows up as a result of a sort of an infinite Markov process where you keep giving root D a chance to check whether it's trivial or not. And the reason why at the end you always terminate with the answer is this equality here. If root D would have order 3, then it's a multiple of every power of 2. But the fact that root D is a 2 torsion element makes sure that if it is divisible by every power of 2, it's trivial. So essentially then the idea is to refine this criterion into a criterion over Z. So x squared minus d y squared is minus 1, solvable over Z now, if and only if root D is in 2 to the k class plus Q root D for all k, for all positive integer k. So in some sense, the solvability over Z is infinitely more complicated than the solvability over Q, namely that you have to go through this infinite process. And something I should have said at the beginning, and let me correct myself now, is that before this theorem, the best results towards Stevenhagen's conjecture were due to Fouvry and Kluners, who could prove positive lower and an upper bound of the right order of magnitude, and essentially they used case 1 and a little bit of case 2. And we can get our theorem because we use every single k. And there is a similar thing going on here in this function problem where each k gives you a better upper bound, and in the limit you get little of x. Okay, but that's simply a criterion. How are you going to make use of it? That's what I want to explain next. Yeah, okay, so I now have to check something for each k. How am I going to do it? And to explain you that, I want to tell you something about Smith's work, because what Smith has done is exactly this. So in 2017, in a work where he also proved something about distribution of two infinity Selmer of twist family of elliptic curves, he proved the following result determined. Let me state it in a way that is closer to that board over there. Determine the distribution of the following vector dimensions F2, and now I'm going to invoke exactly one of the spaces that I want to use to check whether the equation is solvable. Plus 2 root d, 2 to the k plus 1. I will explain in a second. This is k over all integers. So here d runs over imaginary quadratics, square free. That's not the main point here. Because I'm over imaginary quadratics, so then it's fine. Yeah. So there is a similar result that you would get for real quadratics, alternatively both for the, and k here is at least, at least 1. K is at least 1. And this vector, so what is this vector? Here I'm taking 2 to the k, and here there is a 2 to the k plus 1. That means that I'm inside the 2 torsion, because if I multiply 1 more, I get 0. And I am divisible by 2 to the k. So that's exactly what is happening with root d. So here is, root d is here with 4. That's the solvability over q. And the next thing that I'm checking here is 2 square, and here I put 8. 4 and 8. And then I put 8 and 16 and so on. So this is a sequence of subspaces of the 2 torsion, and the negative Pell equation is solvable exactly when root d is stuck in each of the subspaces. So what you are really interested in is the distribution of these spaces. And let me just say a more precise version of his statement. It's a simple algebraic fact that this sequence of spaces, it's just as much data as the 2 part of the double of the class group. The isomorphism type, this sequence of subspaces, the dimension, tells you exactly the type, the isomorphism type of the group. What Smith actually proved, he proved the following, that the probability d is smaller than 0, square free, d smaller than x, the norm, the absolute value of t, and the 2 part of the class group is isomorphic to A, of the double of the class group, isomorphic, which is really suitable for us because we are always stuck inside the double of the class group because the conic has a rational point already. A is a finite abelian 2 group, any finite, maybe Z mod 4, maybe Z mod 16, or the sum of them, or whatever you like, finite abelian 2 group. The probability that this is isomorphic to A is actually equal to C to the product, and that's the same product that was showing up before, but now starts with 1. 1 minus 1 over 2 to the I, that's just a normalization constant divided by the size of the automorphism of A. So that is the best evidence that we currently have for the so-called Cohen-Lenstra-Gert conjectures. For imaginary quadratic fields, the Cohen-Lenstra conjectures postulate that in general the P part of the class group should behave as a random P abelian group, which means exactly this. And over function field, there is some sort of work, some sort of evidence coming from work of Ellenberg, Venkatesh, and Westerland using topological methods, but still it's for the Q, for the limit Q going to infinity, while this is over Q and tells you that, okay, you have to take the double, but then it really equidistributes in the space of abelian groups. And what Smith actually does is not this, but is this chain of spaces, which is then really suitable for the method because we are now in a special family where this is already solvable over Q, which means that D has this restriction on the prime factors, but now you are trying to check whether I am in each of the next spaces. So how does he actually prove this? So what are the main ideas? The ideas is that the ingredients are the following. First of all, and here I'm talking about imaginary quadratic field, so I don't put a plus, otherwise I have to put a plus. Let me put a plus because it doesn't make a difference for imaginary, and this holds also for real quadratic. We have a very concrete description of the two torsion. The two torsion and the dual two torsion. We know these two spaces very well. So this goes back to Gauss. And the description is simply that this is generated by the primes above a prime dividing the discriminant. Let me say discriminant of Q root D. Well, in case D is odd and 1 modulo 4, then this would be really prime dividing D. So you take the prime above, and then the factorization tells you that P square is P, which means that it's two torsions. So that Gauss tells you that those are all the two torsion classes that you can get. The obvious one are all of them, and there is a unique relation among them, and the negative Pell equation is exactly checking whether the relation for a real quadratic is that the product of all of them is trivial. And here you also have, this is the dual group. This symbol here means dual, so you map it to the unit circle. And now you take characters, quadratic characters coming from Q, so you add the square root of a prime, P star. You put a little sign in case it's 3 mod 4, and still P dividing the same thing. And so that's the basic thing that sort of makes the two part of the class group special. You don't have anything like that for the 3 part or the 5 part, but the 2 part, the two torsion at least is very explicit, and it's huge. So for a typical D up to X as log X prime factor, so you see that this space is sort of gigantic, which is the reason why you have to double it, because you have to kill off this space, and then the rest is equidistributed. And so the basic idea to go on and to get this sequence of spaces that encode the group is a pairing. So there is now a pairing. The first pairing would go from here to F2. And the first pairing is the naive pairing. You take A and chi, and you map it to chi of A. And the point of this pairing, which I called Art1, this pairing here, I call it Art1, is that the left kernel of the pairing, Art1 is this pairing, the naive pairing of D is the next space. So this is left and this is right for me. So this is two times the thing is the next space you are after. And dually for the right kernel. And then there is a next one. There is a next pairing, which is R2, which still goes in F2. And here it's a little bit less naive. Namely, the next pairing is defined that you take an element here, and you lift an element here by multiplication by 2, and you evaluate like here. And it has exactly what you think, that the next left kernel is 4 times 8. So these spaces, if you take also the dual, each of them determines the next through a pairing. And then what Smith actually does is to determine the sequence of Artin pairing on these spaces. So the first Artin pairing is actually very explicit, is the matrix of Legendre symbols. Because you have, it's not hard to check that if you evaluate this, you're checking basically P on Q for 2 primes dividing D. So and that's a huge matrix, but the next matrices, they will be typically small, because the first space here will be small, and what he actually does is to determine the distribution of these pairings. And what you want to do here is to determine whether root D is in the left kernel of all the pairings. So a difference with Smith work is that since you are running in this special Pell family, you have a pointed privileged element which is root D, and you are chasing this element, and you are trying to prove that it's in all, it's a killer in all the pairing. It's in the kernel of all the pairings. And that creates actually one of the 2 main difficulties. The other one comes from the fact that you are in a family where all the prime factors are 1 modulo 4. And that makes this first matrix, if you think about how quadratic reciprocity works, this is a matrix of Legendre symbols, then if the primes are 1 modulo 4, if you swap the symbol, you get the same Legendre symbol. So that means that this matrix is symmetric. So that means that these first 2 spaces are the same space. And that is very bad for the rest of Smith method, there were 2 problems. 2 problems. Chase the special element root D in this sequence of Artin pairings. And the next problem is that 2 times class plus 4 is actually equal. When you view it as a space of divisors of D, is actually equal to the dual one in the Pell family, in the family D in SQX. And how much, so when did I start actually at 30? So do I have 10 minutes or? Okay, great. Okay, so I now want to explain so what is the next big ingredient in Smith? How does he actually handle this sequence of pairing? And why these 2 things are very unfavorable, and in his case, he could just sort of disregard it because he was in the natural family of all square-free discriminant. Now we are in this special family, which create the problem that I want to explain to you. So how did he handle this sequence of pairing? Let me explain it first by the next pairing. So this one I told you is a matrix of Legendre symbol. Let me tell you something about this pairing here. So I'm going to explain something about, and then I can say how the story goes on. 2 class plus Q root D, 4. So this is the next pairing. 2 class Q root D. Dual 4 in F2. So this pairing will tell you which elements are multiple of 4. So once you do this, you will discover that root D, after all, was a multiple of 4. So for instance, if you discover it's not a multiple of 4, then you know that the negative Pell equation, you have already done something about negative Pell. So let me tell you actually what this pairing is. So you take an element A, in this, and an element B living in this space. And the pairing actually sends it into a certain symbol, which is called the Rayleigh symbol. And it's the following symbol, A, D over A, and I will tell you something about this symbol. So this is a trilinear symbol. Rayleigh in the beginning of 20th century defined a trilinear symbol on A, B, sending triples of square-free integers A, B, C into F2. And to be able to define the symbol A, B, and C must satisfy a certain condition, which amounts to the fact that A, B, V, the Hilbert symbol is 1. All the Hilbert symbols are pairwise 1. B, C. So a bunch of conics, 3 conics must be solvable over Q. The one ax squared plus by squared, ax squared plus c, and by. Once you have these 3, this vanishing of Hilbert symbols, then he was able to define a symbol which is a bit asymmetrical. It's defined as an Artin symbol of C in a field depending on A and B. And what Rayleigh proved is that this symbol, it's called Rayleigh reciprocity. Raleigh's reciprocity is that this symbol is completely symmetric. Completely symmetric. So despite the definition is quite asymmetric, you can swap it, and then you get the same answer in F2. So the reason why this symbol is relevant is because it's computing, that's not very hard actually from the definition, it's really computing an Artin pairing. It's a symbol that is defined independently of class groups, and it turns out that it does tell you what the Artin pairing of A and B is. And not only is symmetric, and what is actually easier to prove is trilinear. Trilinear, which means that if you take now A1 and A2, and here you leave the same B and C, then the sum of the symbols is the same symbol as A1 times A2 BC. Trilinear A1 BC, A2 BC. It's equal actually to A1, A2 BC. But you have to take the square-free part of that. And I cannot explain one of the key ideas in Smith's work for the second Artin pairing using these facts.
Symbols, I mean, are they symbols in like the sense of K theory?
Sorry.
Are they symbols in the sense of K theory?
That could be. I'm not exactly sure. By symbol here, I simply mean that it's called a Rayleigh symbol.
Okay,
but,
okay.
No, I don't know if they have a K-theoretic.
Is the question whether they factor through some sort of tensor cube or?
Yeah.
I don't think so.
Yeah.
Sorry, how is it defined?
Yeah, it's actually defined as follows. You take a conic, you know by definition that the conic ax squared plus by squared is equal to z squared is solvable, and then you choose a primitive solution to this equation, and there are some choices involved, and you create the field where you add to Q root A root B. You create a dihedral field corresponding sort of to the cup product of A and B, which is taking the square root of a solution. So z minus, I guess, z minus root B y for a carefully chosen solution, and then you take the Artin symbol of C in there. When they are coprime, that's the definition actually. The Artin symbol of C, you prove that it lands in the center, so it's an element of F2. This is a dihedral extension of Q of degree 8, so it's very asymmetric. It's quite surprising that it's actually symmetric, because the definition is very asymmetric. Well, the fact that it's trilinear almost follows by definition. Okay, so now the idea is that you want to use the trilinearity to find relation between Artin pairings. So suppose that you put yourself in a box where you have P1, P2 times, P1, P1 prime, P2, P2 prime, times P3, P3 prime, and suppose that A and B times D. These are primes that they can vary with a bit, so there are 8 integers, 8 square free integers. Is a product space, and suppose that A is supported in this 3 set here, and then it has something in the 0. So A is pi 1. So A is either P1 or P1 prime, is in P1, P1 prime times A0. So A varies now. I have choice of A in D0, A0, where A0 is fixed, divides D0, and likewise for B, I have that varies in an independent bit, P3, P3 prime, times B0, where B0 is also fixed. Now, using trilinearity, it turns out that if you sum the Artin pairing of this field over this cube, so the sum of x in, this is a cube, x in C, of the Artin pairing of A of x and B of x, and that's very nice, you get a Rayleigh symbol that completely cleans off this D. P1 prime, P2, P2 prime, P3, P3 prime. And now the idea is the following, that you have found a relation between the Artin pairings, which is a symbol that doesn't depend on this integer D, but depends also only on these small primes here, this small set of primes here. And now you can think sort of pictorially the situation as follows. You are making a big grid where you are told, in each square, you are told what the vertices are summing to. You are told the result here. But you are not told actually what the vertices are. And if the grid is filled in a very stupid way, like you put all zeros, you can't possibly know anything meaningful about the vertices. They could be all 0, all 1. But if the grid is filled in a random way, and that's how you're gonna use Chebotarev in this relation to make sure that the grid is filled in a completely random way. If you take a generic choice of the filling, then a little Ramsey theoretic proposition shows that whatever is the value of the vertices, if it satisfies this law, it must be equidistributed. It must be roughly half-half. So you can make this precise. For every epsilon, then for most choices of the filling, there is a way to, every choice of the vertices filling that satisfy this rule, which is this relation here, they must be equidistributed. So the equation itself doesn't determine the pairings, but it's enough to prove that the pairings are equidistributed. That's one of the biggest ideas is made work. And his next big idea was to generalize this to higher Artin pairing. So for higher Artin pairings, he defined a generalized Rayleigh symbol, A1, A2, A3, A4, where he proves a relation in a cube, that time with 16 elements. And then with 30, there is a higher Rayleigh symbol with 5 entries, giving a relation with 32 elements. And then the combinatorics is behind is roughly the same. It gets a bit more complicated when you increase the size of the cubes, but the basic idea is this one, and these two are very problematic for this idea, because when you check if the pairing with root D, here instead you get -1. And then for Rayleigh reciprocity, it's very good that you can swap, because then you can apply Chebotarev to this entry. And for the higher Rayleigh symbol, Peter and I introduced a higher version of Rayleigh reciprocity, where you can swap the last 2 entries and you can still apply Chebotarev. And the last problem, you see it already in action here. You see that I had to choose A and B very disjoint. I had to choose A here and B here to apply trilinearity. But if A is equal to B, I get into trouble, and that's exactly what is happening. Sometimes you have to have A equal to B. And we needed sort of a second reciprocity law that has this shape. Yeah, 0. I am finishing basically. Now we have to prove for higher array symbol that when you put the same entry, the symbol is 0. That it's something that works from 4 on. And yeah, sorry, that's, I will stop here. Yeah.
Excellent. Thank you very much, Carlo. Does anyone have any questions? Remember to knock if you have a question.
About your, I think it's the one with Alex Bartel. So it took me a while to understand it, but it was about the image, keeping exactly plus minus 1 plus minus epsilon.
Yeah.
Can you say anything about probability of image being something?
And the thing is that so the global units are z times plus minus 1. So essentially, you have one fundamental unit. You pick one fundamental unit and you check what's the Legendre symbol modulo prime, for instance. It's a bit as if we are doing a equidistribution of Legendre symbol of fundamental units in some sense. Yeah.
Thank you.